Greetings to one and all. I'm Karn from NIT Trichy, and I'll be talking about a novel method of producing ultra high strength yet ductile steels. The strength and ductility are two key factors for a material, but are often mutually exclusive to each other. Therefore, achieving a balance between them has always been crucial. The aim of this project is to conceptualize a route based on the same motive to produce steels that are ultra strong, ductile, are prepared by an energy efficient and cost efficient route. Now, usually, a high strength steel contains dopants. Now, these dopants, although strengthen the material, also adds to the additional costs, and a carbon content of more than 0.48% creates problems in processing, such as during welding. One way out can be by using dislocations and chemical boundaries, which we will see later. The route proposed here studies the expected changes in a medium manganese steel with around 2% aluminum. However, other alloy steels are also expected to show similar results. Now, grain boundary engineering has been there for a long time and has been successful in enabling us to tune mechanical properties. However, their effects are largely limited after nanoscale. Therefore, the present work proposes an idea to use defects such as dislocations to create a heterogeneous microstructure that would hinder slip propagation and therefore strengthen the material. This is an illustration of the proposed heat treatment route. The material is to be hot rolled at about 1150 degrees Celsius, followed by warm rolling at about 750 degrees Celsius, followed by intercritical annealing at about 620 degrees Celsius for 5 hours, followed by cold rolling. It is then to be heated at a rate of about 100 degrees Celsius per second and till it reaches a peak temperature and is immediately quenched, followed by a low temperature partitioning. Now, hot rolling would create a heterogeneous mixture of austenite and ferrite. We'll see about this in more detail in the microstructure slide. Warm rolling further enhances this heterogeneity, introduces dislocations in the austenite grains, and also elongates the prior austenite grains in the rolling direction, resulting in further grain refinement. Following that, intercritical annealing would relieve the residual internal stresses of the material, therefore preparing it for the deformations required during cold rolling. And cold rolling is important because most of the martensite would form in this step via the deformation-induced martensitic transformation, which results in significant increase in the number of dislocations. And then the fast heating and quenching results in rapid elimination of all austenite and ferrite phase boundaries and grain boundaries. And because the process is so fast, diffusion is not prominent. Rather, sluggish diffusion happens, which would preserve the spatial distribution of manganese, would lock austenite into some micron domains, which would be called non-equilibrium chemical boundaries. Concludingly, tempering at a temperature of 400 degrees Celsius would increase the carbon content of austenite, therefore stabilizing the austenite microstructure during partitioning. Now, after hot rolling, we can expect this kind of microstructure, which will be heterogeneous, comprising of coarse austenite, some amount of ferrite, and recrystallized austenite. Upon warm rolling, this austenite grains are further elongated or even fragmented into smaller ones, resulting in grain refinement. There are dislocations introduced. Overall, the structure is more heterogeneous than it was before. And after intercritical annealing and cold rolling, what we can expect is a dual phase lamellar microstructure with austenite grains embedded in martensite matrix. We see that the elongated austenite grains are further elongated here, and upon then heating it at a high rate and then quenching it rapidly, we can expect the ferrite and austenite grain boundaries to disappear at the peak temperature, and then formation of chemical boundaries inside the coarsened grain boundaries during quenching. Upon comparing and contrasting the expected mechanical property of the steel processed through this route with the ones prepared from the existing one, we can expect plots similar to this. We can see that the steel processed through this route would get a distinguished place in the plot because of the new pathway followed. The reasons responsible for the enhanced properties can be the intensive dislocations and heterogeneity developed during hot rolling and warm rolling, the martensite formation during cold rolling, formation of chemical discontinuity during fast heating that would stop the martensite growth by acting as a barrier, and the ultra fine martensite network that would isolate the austenite in some micron domain, therefore restricting the dislocation pileup, the pileup that would in turn hinder slip propagation, therefore increasing the stress values, and the trip effect, which would ensure good ductility. With that, we saw how a new heat treatment pathway that would use defects such as dislocations and chemical boundaries can produce steels with an ultimate tensile strength of more than 2.2 gigapascals with a total elongation of more than 15% at a reduced material cost. These are the references I used to develop the study and to come up with my proposed idea. Thank you for listening. Stay safe.